Hi and welcome to the Science Cottage. Now, when you do electric circuit problems, you do calculations using the potential difference, the current, and the resistance in a circuit. What exactly is potential difference, current, and resistance? In the following video, I'm going to explain that to you. Okay, so let's start with V, the potential difference in volts. One of your equations will look like this. That means that the volts or potential difference measured in V for volts is W is energy, so it's the amount of energy in joules per every Coulomb packet of charge. And the symbol for that is C for coulombs. Right, so a Coulomb packet of charge is a whole group of charged particles. In this case, it is electrons with a negative charge. We don't talk about every single electron. It's more convenient to talk about a Coulomb group of electrons at once. All right, so the battery provides a certain amount of joules per every Coulomb packet of charge. The chemical energy in the battery is converted to electrical energy for these Coulomb packets of charge. The battery doesn't provide electrons. There are already electrons in the metal connecting wire in the circuit. The battery just provides a certain amount of energy for these electrons to move in the circuit. For a 1 volt battery, it means that there's 1 joule of energy for every Coulomb of charge. Let's say this is a 12 volt battery. It means that there will be 12 joules per every Coulomb packet of charge that moves along this circuit. Okay, so we know that electrons actually move from the negative pole where there's a greater concentration of negative energy, and they move from negative to positive. But I'll just talk about this later again. Conventional current is from positive to negative, because when scientists first started studying circuits, they didn't know that it was electrons that moved. So they just chose the conventional route of positive to negative. And all subsequent calculations in electrodynamics and so forth are based on this assumption that current moves from positive to negative. So that won't change. That doesn't change, even though our knowledge of the movement of electrons has changed. So the current moves from positive to negative, but just bear in mind that electrons actually move from negative to positive. Okay, so the 12 volts provided will be exactly used up in the circuit. No more, no less. Looking at the circuit, we just then have to identify where's the main circuit and where are the parallel branches. So that's the main circuit going through the first resistor, and whenever there's a split in the circuit, those are the parallel branches. So marked in green is the parallel, we call it the parallel combination. And the rest of the circuit is the main circuit. The circuit that flows through everything outside of parallel and through the battery. So that is the parallel combination. Okay, so just a few rules regarding the number of volts. Volts will be used up when these packets of electron, the Coulomb packets, move through specific components like resistors, light bulbs, heaters, and so forth. A certain amount of joules for every Coulomb will be used up and converted to another type of energy. In a light, it will be light energy. In a buzzer, it will be sound energy, and so forth. So, you can see here where the circuit splits up into the two parallel branches. Here is no component using up joules per Coulomb. So all of the Coulomb packets that travel into the top branch will get a certain amount of joules per every Coulomb, a certain amount of volts, and the Coulomb packets of charge that will move into the lower branch will get the same number of volts. Again, because there's nothing at this junction that uses up any volts. So the first rule is volt. Potential difference for each branch will be the same. But now in series, in the series circuit, this main circuit outside, or when two resistors are in series with each other. In this case, the battery is in series with the first resistor, which is in series with the whole parallel combination, in series with the fourth resistor, and in series with the fifth resistor. So we have a 12-volt battery. In this first resistor, 4 volts will be used. For the parallel combination, 3 volts available for parallel, which means that the top branch gets 3 volts. The lower branch gets 3 volts. 4 and 3, 7, so it means that there's 5 volts left for those resistance if we don't take into account the internal potential difference that the battery uses. So if that one uses 3 volts, then there's 2 volts of energy left, 2 joules left for every Coulomb packet of charge that moves through that resistor. So volt is split up, or potential difference is split up in series through the series components. All right, so just again, the battery provides joules per Coulomb, it provides potential difference, and then the components use up the potential difference, and all of the branches in parallel get the same amount of potential difference. 3 is equal to 3 is equal to 3 is equal to 3 is equal to 3, because at this split, there's nothing that will use up any volts. That doesn't mean that there's 3 plus 3. 3 is equal to 3. The volts did not get split up into 2 groups of 3. All right, so the next thing that we'll look at is the current. An equation for current looks like this. Every time that time is below the dividing line, it means rate of, how fast something is happening. And we've seen that Q is the charge in Coulomb. So the current, measured in amperes, is literally the rate at which these Coulomb packets of charge move, how fast they are moving. And we've mentioned earlier that the conventional current moves from positive to negative, even though the electrons actually flow the other way around. Right, so it makes sense that the higher the amount of volts, the higher the amount of energy per Coulomb packet, the faster the current will be, because there's more energy available for movement of the electrons. So volt is directly proportional to the current. Okay, just rules regarding the current. In the series circuit, in the main circuit, the current will move equally fast everywhere in the main circuit. So in other words, through that resistor, through the battery, through those two, the current will be the same. Right? It's like a bicycle chain. It can't move faster in one place and then slower in another. In the series circuit, the current is equal everywhere in that series circuit. However, in the parallel branches, the current will split up. Like a river, when it splits up into two streams, the current will also split up. The higher the resistance that's provided, the slower or the lower the current will be. The lower the resistance, the higher the current will be. So in parallel, the current splits up. So it doesn't always split up equally. If the resistors are equal to each other, the resistance in the top branch and the lower branch, then the current will be equal in both. But like I've said, for a higher resistance, the current will be a bit lower. For a lower resistance, the current will be a bit higher. So let's say we have a current through the battery of 6 amperes. It means that the current through the series circuit will also be 6 amperes everywhere in the series circuit, and it splits up into the parallel branches. So if this resistance is high, we can, for example, say the current through that top branch is 2 amperes, which means that the current in the lower branch will, for example, be 4 amperes. So we've seen that the current is inversely proportional to the resistance. The higher the resistance, the lower the current through that specific part, through the main circuit or in a specific parallel branch. All right, so what is this resistance? Resistance is anything that provides resistance to this flow of the current inside the electric circuit. This is what a resistor looks like. And here's just another component of a circuit that can provide resistance, a globe. If you come for tutoring at the Science Cottage, we can build a little circuit using these components, and you can see how they are connected together and what the effect of the connection will be on the circuit. So think of the N1 highway. If you hear that there's a stationary truck a kilometer in front of you, and then just after that there's an accident, and just after that there is a police blockade, the more resistance in series, one after another, will make the whole flow of the current slower. So in series, all the resistors are added together and they lower the current in the main circuit. So over here, the current specifically measured through the battery and through the resistors outside of the parallel combination will be lower if we put in higher resistance. Now, in the parallel branches, something different happens. Think of the same highway, the N1. Now you hear over the radio that an alternative route is available. That means that the current of cars will split up into those two paths, and in total the stream of cars will get to wherever they want to go a little bit faster. So the more branches we add in parallel, the faster the total current will be. We've seen, and it's still true, that the higher the resistance inside one branch of the parallel combination, however, the lower the current will be inside that branch, inside the separate branches. But in total, the total stream of cars will get to where they want to go a little bit faster. So the total outside of the parallel combination, the current will be higher if we place more resistors in parallel. Now, what does this resistor do? It doesn't change electrical energy into anything kind of useful for us. It doesn't change electrical energy into light or into heat or into sound energy. So what's the point? So a resistor in a circuit is used to modify how fast the current flows. As you've seen, more resistors in parallel, the higher the current will flow. Now you might ask, if we want the current to flow really fast, why just not put in any resistors? The reason for that is, just imagine when you rub your hands together, you will feel, due to the friction, some heat energy is generated. Now exactly the same happens in a circuit. The faster the current flows, the greater the heat energy that is produced. So if we have, for example, a branch in parallel with no resistance, the current will choose the path with least resistance. It will move so fast that the wire will melt and a short circuit will occur, or I don't know if you've seen this before, like a little explosion at the plug point or at the light bulb that you're using or whatever, because a short circuit occurs. So a resistor is necessary to modify that current. If you just set up a circuit without any resistors, the battery and everything will short circuit. All right, so in parallel, your calculation will look like this. So mathematically, the more branches there are in parallel, the lower the total resistance for the parallel combination will be, and the higher the total current will be, in other words. All right, so let's just have a look at how these three can be combined mathematically. So the resistance, you will see this equation on your formula sheet. All right, so resistance and current is inversely proportional. They are inversely proportional to each other. The higher the resistance for a constant potential difference, the lower the current will be. Also, if we just rearrange this equation, you see that the potential difference is directly proportional to the current. So the higher the potential difference, the more joules given by the battery to each Coulomb packet of charge, the faster the current can flow. And then also here you can see that the current and the resistance are inversely proportional to each other. So the higher the resistance, the total resistance, the lower the current will be. And the lower the total resistance, the higher the current will be. All right, so in a nutshell, that is what is meant by V, I, and R. Keep on following the channel for some more videos on electric circuits and electricity.